Hi everyone, I'm Clément Labrugère from Mirakl, and I will be joined with Mehdi Elion today. We're going to share some of what we are doing at Mirakl, and in particular how we use transformers at scale to boost recommender systems. So it's a bit in the same continuity to what Xavier talked about just before, just not that advanced with the agentic yet. How do I pass it? So a lot of people think that ads in general boils down to whoever pays the most wins. Well, while partially true, if we were to do that, actually we will be losing money, or not that much money, and you would have a terrible user experience on the website. Fundamentally, ads, especially on e-commerce, it's about balancing, maximizing the revenue for the customers, so the platform and yourself, but also making sure that your users have the best experience. So on the one hand, you have an advertisers that pay a premium to get the top spot on an e-commerce website, but he pays only when there is a click. And on the other hand, there is a click from the users only when they are genuinely interested in the product that you show them. So here we will talk about personalization, because it's really a win in this kind of situation, because it bridges both requirements. But it's not that easy to do in practice, especially at scales, because, well, you cannot have your user wait for seconds before you render a page, right? Otherwise, they just leave and you lose the potential revenue. You also need to serve millions of users a day, potentially. Finally, you also need to work over very large product catalogs, some of them exceeding the tens or hundreds, millions of products. So how do we build this kind of system? Well, first, let's take a bit of altitude and see generally that recommender system in AdTech specifically, there can be abstract roughly in 3 main steps. So let's say you go to an e-commerce website, you are looking for something, and you go to a product page. It will trigger what we call an add request that we first need to hydrate, which means simply adding a bunch of contextual information. And in particular, the browsing history of you as a user on this platform. Now that you have that, comes what we call the retrieval part. Which is really just about finding the most relevant products given the context. So your history, for example, or you as a user. Now here it's a bit tricky because we need to go from, as I said, millions of products to a couple hundreds max in a matter of a few milliseconds only. It needs to be very fast. So speed is of the essence here. Then once you get this kind of candidate products or recommendations that you want to make, usually we will nudge, reshuffle them slightly to take into account the product performance. So it can be, for example, the popularity of a given product, but also its virality, let's say. And as is tradition with ad tech, we also put in competition the advertisers. And this takes place in the form of some kind of auction. So for example, the first price auction that will re-rank a bit this order. So in the end, yeah, if you bid more, you are a bit more likely to be on the top, but it's just one part on a much more complex equation. Now let's zoom in a bit in how we find these relevant products, especially at scale. So, as you might imagine, browsing history carries a lot of information. It's not a secret, but actually you don't need that much history to make it very useful to already boost the recommendations by an order of magnitude. But before going into that, first you need to encode your products, right? So here it will be a bit more technical, but don't worry, it's going to be fine. You need to encode them. So here you can use, for example, what we use is a custom trained model plus some kind of fine-tuned multimodal encoder that is frozen in order to produce strong and rich representation of our products, vectors really, that can encode both the content, so the content of a product, for example, a particular dress is red, this kind of information, but also encode the macro behavior of your users. And we'll come back to that a bit later. Now, once you have these representations, you need to store them, right? So usually we will use an approximate neighbor search index, which is just a fancy word for a database that is specialized on this kind of payloads, right? But here the important thing is that you need to keep that in synchronization with your product catalog, because as I said before, if you are not able to serve recommendations for a given product, it means that you lose a revenue potential, and you still pay for the infra, so it's really a loss here. Now that you get that, let's say what happens at runtime. So let's say you're on this product page, you trigger this add request. Well, we hydrate that first. We can fetch the user history from a hot storage in a matter of milliseconds. It's very fast. Then we can deduplicate that, obviously, the user history, and we will perform a bunch of parallel queries on this index. So that's, let's say we take the product you are currently seeing, we try to find the most relevant product to this one, then we take the product that you've seen before, we do the same, and so on and so forth along a given history. Then when we get that, we apply some kind of mixing function. So it's really like a Bayesian policy, which can be interleaving the results by recency and relevance, for example. It can simply be concatenating them, you name it. At the end, you get a final set of recommendations that can be like reshuffled slightly to take into account the performance and the bid, as I mentioned before. Now I want to share some of the source that we use for the user model in particular. I'll try to keep it digestible. I hope some of you are technical, because otherwise it will be a bit rough. But in a nutshell, it's a transformer-based model that is learning sequences to learn product representations based on user sessions. So the model itself is trained in a self-supervised fashion, which means that we take product sequences, consider like a very big history from a user, we chunk that into sessions that should contain higher intent, and from that, it's great because we don't need actual labels, actually. We don't need to collect clicks or whatever. The view themselves, the tracking itself are the labels. And we get plenty of data for that, compared to the sparsity you can have with explicit feedback sometimes. Now, to boost a bit on the generation side, we also use complementary information. It's not just like product sequences. In particular, we can use the category information, for example, and this is very helpful to learn strong representations for tail items, which are products in your catalog that don't see much traffic, but you still need to recommend them for diversity's sake, for instance. Now, going a bit further into the generalization, we also have to initialize randomly these product representations you would normally do, but instead we use the results of this multimodal encoder in order to capture some of the interesting attributes of the product. For example, the color, the texture of clothing, or for example, some attributes on cell phones, stuff like that. It has many benefits, but three of them are, first, it makes the representation richer and makes the model converge faster. It also helps on the generalization for tail item, because you can only encode so much with only behavioral data, right? How can you infer that a dress is read with a sequence of products? It's not really possible. And finally, a very nice property of doing that is that it gives us a very natural way to handle cold start. Which is simply the phenomenon when you don't have any signal for a specific entity, but you need to take it into account still. On a slightly different topic, this is more like a trick applied to our business, but usually we want to recommend similar products and not only the products that are viewed together, right? And so here we can implement some kind of structure in the model by a small regularization scheme that try to push the products toward their category. So they will orbit in the latent space around the categories, let's say. And this is nice because when you want to answer another request, you will be more likely to have candidates that are that belongs to the same category, and in practice, it can improve the relevance. Now, as I mentioned a bit earlier, we also need to work with potentially very large catalogs, millions of products, even more. So, for you that are a bit technical, you will know that it's not very practical at all to model the embedding tables and the projection head, the classification head, over very, very large vocabularies because of simply the memory constraints that you have on your machines. So we use a bunch of scalability hacks, but two of them mostly I want to mention is first the use of specialized open source library, which is maintained by Facebook actually, that allows us to reduce the computational, the memory footprint mostly of the embedding tables, but up at 75%, which is very big on large catalogs, and also the use of sample softmax, which is like the last computational part when you want to product your predictions that make it possible to avoid the classification head altogether. So you have this more or less the same order of magnitude of savings. So as a result, we're able to train models covering, let's say, 1 million products on consumer-grade GPU, not even distributed for such catalogs, in a couple of hours. So it's very memory and computationally efficient, and it allows us to train these models very frequently, or simply to not spend a humongous amount of money on just that. Okay, so over with the technical stuff. What about the real-world performance? As you can imagine, we didn't deploy that on all the traffic at once. So we initially performed an A/B test thanks to our experimentation platform over the last year, and we did see significant uplift. So in both click-through rate, which is just the average click-through on a given item, by around 30%, depending on the customer, and also the revenue. So this is the most significant one, because sometimes the click-through rate and revenue are not totally correlated, by about 35%. So this kind of approach really means that we are able to deliver much more relevant recommendation in the context of retail media advertisement. So this is something to keep in mind. But also, so we are able to generate more revenue, as you can see, but also because we are able to deliver more relevant recommendation, it also means that we don't impact the user experience, and on the contrary, most of the time we improve it because the products can be found more easily by the user on the platform. And as a side note, the advertisers are also happier because they get better return on their ad investments, but okay. So this kind of thing, of approach are now used for ads customer across the board, and it keeps delivering very good results, especially in high intensity periods such as Black Friday or the Christmas sales. Now I'll hand it over to Mehdi. We'll share a bit more how we're trying to push personalization in even further. Thank you.
Thanks. Okay. So we've seen how to use transformers to produce powerful product representations. But we wanted to take it a step further and explore other ways to take advantage of those models. So we dug into the next product prediction use case, in which a model is trained to predict the product coming next in a user session. So this is basically the learning task for the training phase. And now for the inference phase, once the model is trained, the idea is to use its predicted click probabilities to re-rank a set of candidate products. And this would typically happen downstream a retrieval stage, which produces the set of candidates. And of course, such an approach would require the model to be served for live inference, as each user session is unique and triggers an ad request, which requires an immediate answer. Okay, so as mentioned before, here we want to share one of the tricks which made things work for us. So in terms of modeling, we would typically address this problem using cross-entropy loss, but this would involve computing a softmax over a very large set of products, let's say 10 million or even 100 million products. And without going much further into the details, it would be computationally expensive and it could hinder the model's training procedure. So instead, we opted for samples of max loss, which in simple terms consists in computing the loss over a subsample of products made up of the true next product, marked as positive, and a certain number of randomly sampled dissimilar products, which are marked as negative. And overall, it makes the training procedure stable, faster, and more memory efficient by saving approximately 2 gigabytes of VRAM per million products. So this is one of the tricks we use to make the training robust to large catalogs. So we're still in POC phase regarding this topic, but we already have a few figures to share. Starting with the training part. So it takes approximately 2 hours to train a model on approximately 3 million user sessions, which is quite reasonable. And it also fits in a single NVIDIA A10 GPU with 24 gigabytes of VRAM, which is possible thanks to the optimizations we've mentioned before. As for the inference part, we carried out a few offline tests to measure it. And it turns out that it takes less than 10 milliseconds to run a model inference on CPU, which is possible thanks to the shallow architecture of the model. And finally, regarding the performance of the model, we carried out an offline estimation of the hit rate at 10 using a set of about 200K user sessions. And we found out that in the best cases, we could obtain up to a 30% lift in hit rate at 10 against some of the approaches that are already in production. So we believe it's a pretty promising approach. Okay, so now it's time to wrap things up with a few takeaways. So the first message we'd like to share with you guys is that personalization is a must-have, not a nice-to-have, as it boosts significantly a recommender's performance. We've also shown that for personalization, transformer models could be efficient and scaled across a diverse set of marketplaces, thanks to some key optimizations. And finally, we'd like to end this talk by saying that we're convinced that personalization will remain a key component of efficient e-commerce stacks, especially agentic ones, actually, which we hear a lot about these days, for which the explicit user intent and the low number of placements will offer even more opportunities for personalization. So that's it for this talk. Thanks for your attention. Just so you know, we're currently hiring, so feel free to check out our careers page. And of course, if you want to, feel free to reach out to us if you want to get in touch or have any questions. Thank you very much.